Hi everyone, welcome to another video for research design and analysis. This is the second video in our series talking about sampling distributions, and in this video we really want to focus in detail on the central limit theorem and how anytime we're sampling from a population, the distribution of sample means is going to start to approximate a normal distribution regardless of what that parent population actually looks like. Okay, so to be concrete, what is the central limit theorem? The central limit theorem states that given a distribution with a mean of mu and a variance of sigma squared, the sampling distribution of the mean approaches a normal distribution with a mean of mu and a standard error of sigma over the square root of n as n increases. So at smaller n's, this will only be an approximately normal distribution, but as n gets larger, it's going to be a basically perfectly normal distribution. And we'll talk in a few more videos about what approximately normal distributions look like. But for now, let's just think about that this is going to become more and more normal as n gets bigger and bigger. And recall that the standard error of the mean is really just a special case of the standard deviation, right? So our standard error is proportional to the standard deviation in the population divided by the square root of n. And the standard error, though, is really just a standard deviation for the sample means. It tells us how much sample means tend to vary relative to the population mean. Whereas if we looked at just sigma, or sigma squared, that tells us how much scores vary, so ignoring means. So the standard error is going to be really important here because it's going to inform just how spread out these distributions are when we're talking about taking samples of different sizes. Okay, so as a reminder then, we're going to talk about the sample distribution first. To refresh that, if you've forgotten some things, go back and watch our previous video. And then we're going to talk about what it means to be a normal distribution. So as a reminder, a sampling distribution is a probability distribution for some statistic repeated over replications of an experiment. So we're mostly focusing on the distribution of sample means, but you can calculate these sample distributions for medians, you can calculate them for standard deviations, you can calculate them for variances, right? But what we're interested in is how that statistic is distributed if we were to hypothetically repeat the sampling procedure, hundreds of thousands of times to a theoretically infinite point. And we're going to show most of these things using simulations rather than deriving them from the mathematics, because again, our goal is really more the conceptual understanding of how these things shake out, not necessarily the mathematical formalisms. I'll occasionally post some videos trying to do the proofs, so you can dig a little deeper into those things if you're really interested. But okay, for the distribution of sample means then, we are specifically talking about the probability distribution of x bar, right, which is our shorthand for the mean of a sample. So we'd like to derive some kind of a density function. So in this case, we're looking at the density of just x's. This is our population distribution. So this is the density of hypothetical x's in our population. And what we'd really like to have is a similar density function, but for sample means rather than for individual x's. So if we're sampling from this population, though, let's say that hypothetically we're taking samples of size 5, right? I can take my first sample, I can calculate the mean. I can take my second sample, calculate the mean, and so on and so forth. And I can do that, a theoretically infinite number of times. In practice with our simulations, we might do it 10,000 times or 100,000 times. But we're going to take these samples repeatedly and then calculate a mean for each of those. And then what we really want to know is the distribution of these sample means, right? So it's not the distribution of x's anymore, but it's going to be the distribution of these sample means. So if we want to look at the distribution of sample means, then we might end up with something that looks kind of like this. So these are some data that were sampled with an n of 50, and this is some simulated weight data. So these were individuals who had a mean weight of 75 pounds and a standard deviation of 25 pounds. But now, rather than looking at the distribution of individuals, we are looking at the distribution of sample means. So the mean of all the means still lines up at 175, but then you can see how the distribution of sample means spreads out in either direction, so that most of our sample means are between 170 and 180, but they do spread out, and so it's not unusual to really get a sample mean of about 165 to 185, but it starts to get pretty unusual to get a sample mean that's much beyond that in either direction. So the mean of means, right, is going to be an unbiased estimate of the population mean. Like we said, the true population mean was 175, and if we were to take the mean of all of our sample means, it's also 175. because again, any individual sample might underestimate or might overestimate, but on average, the mean of our means is 175 because we have an unbiased estimate of the population mean. And each of these levels then of the mean spreads out, and the density changes as a function of how far away from the population mean that we are, right? And that follows the same proportions as a standard deviation, because this is our standard error of the mean. The standard error gives us the average deviation of sample means away from the population mean. And in this case, right, we would have an n of 50, and the population standard deviation was 25, so our standard error would be 25 divided by the square root of 50, and you're going to see a fall off in the proportion of sample means every time you move, a standard error further away in either the positive or the negative direction. Okay, so hopefully that kind of refreshes your memory a bit about what a sample distribution is, and in this case the sampling distribution of means. But now the next part of the central limit theorem, as we said, is that sample distribution of means is going to approximate a normal distribution, especially when the sample size is large. So that begs the question of, what is a normal distribution? Well, technically speaking, a normal distribution has a density function where the density is a function of the score, x, and then you could solve the rest of this equation plugging in the value, the population parameters of the mean and the standard deviation in order to figure out what the density is for a given mu and sigma. Now, what we call the standard normal distribution has a mu of 0 and a sigma squared of 1, which means it also then has a sigma of 1 because the square root of 1 is 1. So this red curve is the standard normal curve. It has a mean of 0 and a standard deviation of 1. The blue curve is a normal curve, but it's not the standard normal curve. It still has a mean of 0, but its standard deviation has gotten smaller. Similarly, the yellow curve is also a normal curve, but it's not the standard normal curve. It has a mean of 0, and its standard deviation is bigger. But it's not just the standard deviation that we can change. We can also change where this distribution is centered. So for instance, the green distribution is also a normal curve, but it has a mean of -2 and a standard deviation of 0.5. The thing that all these distributions share is that their density, right, where you're at on this y-axis, can be solved for by plugging in particular values of x into this equation. The values of sigma and mu are going to change, but they all follow this formula in terms of their probability density function. So these are all normal curves. Conceptually, then, this is where it gets really important, because if we can define the probability density function mathematically, we can calculate the probability of certain events. So for instance, on any of these, 4 curves that we're looking at here, we could say, what's the probability of getting an x between +1 and -1? And it's going to be a different probability in each case, right? So for instance, for the blue curve, almost all of its density is between -1 and +1. Whereas for the green curve, much less of its density falls between -1 and +1. So all of those probabilities are going to be different, right? But if we actually understand the mathematical properties of the curve, then we can solve for the area under the curve that's in that range, and then that will give us the probability of obtaining an x of that value, right? Similarly, we could say something like, well, what's the probability of getting an x greater than or equal to 2? And again, it's going to be different in each of these curves, but we could solve for the area under the curve in this area now, right, and get the probability under each of these normal distributions of getting an x greater than or equal to 2. Because again, if we understand what defines the distribution, we can solve for the area under the curve and then calculate the probability. And now, in practice, applied researchers usually let our computers do these calculations for us, right, rather than doing the calculus by hand. But it's very important to understand the concepts, right, is that we're going to be trying to solve for the area under the curve, and we can only do that if the curve is known and obeys certain mathematical formalisms. We've done this in the past with discrete data, with like dice rolls or coin flips, and now we're doing something very similar, but our data are continuous. So it's related, right? This is very much like what's the probability of getting multiple heads in a row, But the difference is now we have continuous data that can take on a whole range of values. They no longer fall into discrete categories, and the distributions then are a little bit different. These are continuous probability distributions rather than discrete probability distributions. So again, in practice, our computers are going to do these calculations for us, but we really want to spend some time on this because we want to make sure we understand the concept behind what those computers are doing. So the power of the central limit theorem, right? Now that we understand what a sampling distribution is and what a normal curve is. The power of the central limit theorem is that given any distribution with a mean mu and a variance of sigma, the sampling distribution of the mean always approaches a normal distribution with a mean of mu and a standard error of the mean equal to sigma over the square root of n as n increases. So this is really key because that means if we know it's always going to approach a normal distribution, regardless of what the parent population looked like, all we need to know are the characteristics of the sample in order to start to make inferences about the mean out in the population. Okay, and let's break that down a little bit. So here we have two very different looking populations. One is a true normal population with a mean of 100 and a standard deviation of 15. The other is what we would call a uniformly distributed population. So a uniform distribution is fairly easy to understand. You give it a minimum and a maximum, and between that minimum and maximum, all scores have an equal probability of occurring, so it looks pretty flat or uniform, hence the name. So this one has the same mean. It has a different standard deviation. In this case, this has a standard deviation of 40, but that's going to give us an upper bound and a lower bound that are more similar to this normal curve. So these are slightly different, right, populations in terms of their minimum and maximum, but they're clearly very different in terms of how they're distributed. This one is normally distributed. This one is uniformly distributed. Okay, so now, though, let's take samples from each of these two very different looking populations. So again, using simulations, we're going to take 10,000 samples of size 10 from each of the two populations. If we do that, here's our 10,000 sample means plotted for the normal distribution. Here's our 10,000 sample means plotted for the uniform distribution. And you can see that these, regardless of whether it's coming from a normal distribution to begin with or a uniform distribution to begin with, both look pretty normal. And in fact, this one is a little bit non-normal. It's probably a little wider in the tails than a true normal distribution is, but they are both at least normal to approximately normal. And we can see the behavior of some of these things. So across this distribution of sample means, the mean of sample means is 100, right? Because again, it's an unbiased estimate of the population mean. Similarly here, the mean of sample means is 100. It's an unbiased estimate of the population mean. And then if you were actually to take the standard deviation of each of these distributions, you find that this one is 4.75, which lines up with what we would expect from the central limit theorem, where we take our standard deviation of 15, divide it by the square root of the sample size, which is 10. Similarly here, this one has a wider standard deviation because it's much more variable to begin with, but again, it's proportional to what we would expect under the central limit theorem. It has a standard deviation of 12.6, which is equal to the original standard deviation of 40 divided by the square root of 10. So regardless of the distribution that we sampled from, we get approximately normal distributions of sample means down below. Let's scale that up now and increase the sample size, because again, the central limit theorem says that these should be more normal the larger the sample size actually becomes. So we can do that, right? Again, we'll take 10,000 samples, now of size 150, and the first thing that should probably be evident is that these distributions are a lot tighter. So they might look a little funny because we're so far zoomed out on this scale. So this one looks almost like a little, needle point or something. But if you actually zoomed in here, it would look more normal than it actually is. But again, when we're taking this larger sample size, now both distributions, right, sample distributions of the means are normally distributed. Both have a mean of means that's equal to the population mean, and both have a standard deviation that is equal to the standard error that we would expect under the central limit theorem, where the standard deviation of this distribution is 1.22, which is proportional to the original standard deviation divided by the square root of the sample size. Similarly, this one has a standard deviation of 3.26, again, because the standard deviation is so much bigger in the population, but even then, this standard error is proportional to the standard deviation in the original population divided by the square root of the sample size. So this is the really cool thing about the central limit theorem. That it does matter a little bit in the sense that the closer our population is to normal, the more normal the distribution of sample means will be. But regardless of what the original population distribution was, the sample distribution of means will always approach normality in large samples. So this is awesome because it gives us the power then to generalize from a mean we observe in our sample back to the population, because the central limit theorem essentially tells us it doesn't really matter all that much what the original population distribution looked like. We can make inferences about the sample mean provided our sample is sufficiently large. And so we're going to get into more detail about what an approximately normal distribution means. But in sort of any practical sense, once your sample size gets large enough, we can assume that this will be a normal distribution, or so close to normal that it's a fairly trivial difference as the sample sizes get larger and larger. So we're going to use normal and approximately normal distributions a lot when we're working with samples in the future, because again, the beauty of the central limit theorem is it doesn't matter what the original population was, right? If we have big enough samples, it's going to approach a normal distribution of sample means. Or if our samples are smaller, we just have to take into account how much they deviate from the normal distribution. And so we'll go into some detail about how to calculate approximately normal distributions relative to the size of the sample that we're calculating. So now let's think about this and get a little practice with these sampling distributions. Let's assume that we're looking at a variable like IQ, where there's a defined mean and standard deviation for the IQ test, where it has a mean of 100 and a standard deviation of 15 in the population. Now, let's assume we're taking a distribution of sample means where n is 25. We know that that distribution will be approximately normal, because this isn't a really big n, so it's only probably going to be approximately normal. Then we'll take a sample distribution of sample means where n is 100, and a distribution of sample means where n is 400. And now we can look at the expected values in each of these distributions. Well, the expected value of the mean, right, in each case is 100. We expect the mean of sample means to be equal to the population mean, because again, any individual sample mean is an unbiased estimate. So all of the overshoots and undershoots will cancel each other out, and on average, our mean is going to be an unbiased estimator, and that doesn't change as a function of sample size. What does change as a function of sample size, however, is the standard error in each of these cases, right? So when our sample size is only 25, the original population standard deviation is 15. We divide that by the square root of 25, so our standard error is 3. If our sample size goes up to 100, now we take 15 divided by the square root of 100, and our standard error is 1.5. If our sample size is 400 now, so that's getting quite large, our standard error is only going to be 0.75, which is 15 divided by the square root of 400. So we can calculate each of these standard errors and then use that in the description of a normal curve to find the probability of certain events, because we can say, well, how far away is a particular sample mean from the population mean in units of standard error, right? So we can look at this distribution of sample means for each of these 3 different sample sizes. Again, they're all centered in the same place, but their distribution changes as a function of that standard error. So now I could ask you a question, like how likely is it to get a sample mean of 103 or greater? And the answer to that is, it depends on how big the sample is. Larger samples make a 3-point deviation less likely, right? When our sample size is 25, it's not unusual to get a sample mean of 103 or greater. But when our sample size is 400, now it's extremely unusual to get a sample size of 103 or greater. The vast majority of our samples, in fact, fall between 98 and 102. So the size of the sample affects the spread of the sampling distribution, which in turn affects the probability of observing certain events. And the more we know about these distributions, the more accurately we can calculate those probabilities and therefore make inferential judgments about seeing something in our sample.